Two other types of circuit elements are open circuits and short circuits. Short circuits are just perfect conductors. They don't introduce a voltage difference. Open circuits are the opposite. They don't allow any current to flow through them. I'll also introduce switches in this video. Switches just toggle between being an open circuit and a short circuit. A short circuit has no voltage difference between its terminals, which is exactly the same as a perfect conductor. Since there's no voltage difference, no energy is required to move charge through a short circuit, so any amount of current can flow through the short circuit. The circuit symbol for a short circuit is just a line or a wire connecting its terminals. It's the same symbol we already used to indicate the perfect conductors that interconnect our elements, since they're mathematically exactly the same. The voltage difference across a short circuit is zero, but the current that flows through it is not defined. The current through the conductor is set by the other circuit elements that are connected to the short circuit. Keep in mind that we mathematically model all of our circuit elements by the relationship between the voltage and the current at the element's terminals. This relationship is called the voltage-current characteristic. The voltage-current relationship for a short circuit is simply that the voltage is equal to zero for any value of current. Graphically, this corresponds to a horizontal line at V equals 0 on this set of axes. Remember that the voltage-current characteristic for an ideal voltage source looks like this. It's a horizontal line, and the voltage is V sub S for any value of current. This is the same curve as the voltage-current characteristic for a short circuit if the voltage source is 0. A short circuit is mathematically the same as an ideal voltage source with V sub S equals 0 volts. Understanding the mathematical similarities between short circuits and voltage sources will be important to various analysis approaches we'll use later in the class. An open circuit doesn't allow any current to pass through it, no matter how much voltage difference you apply across it. Therefore, the current through an open circuit is 0 by definition. The voltage across an open circuit is undefined. Symbolically, an open circuit is represented by a break between its terminals. In an open circuit, the current is 0, and the voltage difference across the open circuit is not defined by the open circuit itself. The voltage difference is set by the elements the open circuit is connected to. Since current is 0 and voltage can be any value, the voltage-current characteristic for an open circuit is graphed like this. The voltage-current characteristic for an ideal current source looks like this. It's a vertical line, and the current is I sub S for any value of voltage. This is the same curve as the voltage-current characteristic for an open circuit if the current source is 0. An open circuit is mathematically the same as an ideal current source with I sub S equal to 0 amps. Now let's take a look at a quick example of open and short circuits in an overall system. My example has a voltage source here, a current source here, and some arbitrary passive element over here. There's a short circuit here and an open circuit here. When analyzing this system, we know that the voltage across the short circuit is 0, but we know nothing about the current through the short circuit. That simply means that this current remains an unknown when we analyze the system, and its value will depend on the other circuit components. For the open circuit, we know that the current here is 0, but we don't know anything about the voltage difference. So the voltage difference is an unknown when we perform a circuit analysis. Keep in mind the similarity between an ideal voltage source and a short circuit. The voltage across the voltage source is known, but nothing is known about its current. Likewise, an open circuit is analyzed similarly to a current source. The current is known, but the voltage difference is a variable. Finally, I'll talk about switches, which can act as both a short circuit and an open circuit depending on the position of the switch. A typical symbol for a switch looks like this. This arrow indicates the direction of the switch motion. The time at which the switch moves is indicated on the diagram next to the switch. This switch is moving from this position in this direction at time t equal to 0. When time is less than 0, the switch is open, which means it acts like an open circuit. This means that for t less than 0, the switch doesn't flow any current, but it has an undefined voltage difference. For time greater than 0, the switch is closed and there's no voltage difference across it, but we don't know anything about the current through the switch. In the next video, I'll introduce another type of circuit component, resistors. After we talk about resistors, we can talk about the laws that govern interactions between circuit components, Kirchhoff's current law and Kirchhoff's voltage law.